My name is Leah Trigg, and today I'm going to talk about the impact of shipping noise on the diving behaviour of grey seals. With the globalisation of trade, the world has been building more ships, and there are now over 94,000 in the world's commercial fleet. This has led to an increase in low-frequency underwater noise in many regions. As you can see, there are few parts of the ocean untouched by shipping, and the resulting noise is now a chronic pollutant. There is evidence that this can have a negative impact on marine mammals through mechanisms such as communication masking, changes in behaviour, and physiological changes such as an increase in stress. For Phocid pinnipeds, such as grey seals, their functional hearing range is thought to overlap with the sound emitted from ships. And in the UK, within 50 kilometres of the coastline, there is significant overlap between seal habitat and shipping lanes. Studies of seals hauled out on land show they will enter the water and display alert behaviour when disturbed by approaching ships. However, we know much less about how they behave in response to shipping noise when at sea. It is predicted in the English Channel and Celtic Sea, 24-hour exposure levels of grey seals to shipping noise could be between 118 and 152 decibels. As air-breathing mammals that forage at the bottom of the ocean, diving is key to the life strategy of grey seals. The behaviour enables activities such as foraging and travel. It is an energetically complex process, and disturbance could have implications for individual level success. As a result, we investigated the impact of shipping noise on the diving behaviour of grey seals. Diving behaviour of seals was collected using GPS/GSM fast lock tags on 16 seals, 8 pups located in the Celtic Sea and 8 adults located in the English Channel. Dives were characterised by a series of metrics. These were dive duration, maximum dive depth, ascent rate, descent rate, bottom time and inter-dive interval. The level of shipping noise experienced by each seal was predicted using a noise modelling approach. AIS ship location data was combined with the Randy model of ship source levels. The location of the seal was given by the GPS tags, and the loss in acoustic intensity as the sound travelled between the ship and the seal was calculated using a range-dependent acoustic propagation model called RAMSURF. From the received weighted sound pressure levels, the noise metric maximum sound pressure level was extracted for each dive. The pervasive nature of shipping noise means it's hard to find times when there is no noise exposure. Therefore, dives before, during and after noise events were in the seal track. High noise events were those above the 95th percentile, and the same number of dives before and after these events were extracted. Generalised additive mixed models were used to model the dive metrics as a function of the explanatory variables noise category, so before, during or after a high noise event, dive class, whether dives were benthic, pelagic or shallow, and bathymetry. The nested random effect of seal and event were used to account for correlation within these seals and events, and post-hoc analysis of the different noise categories was conducted by comparing the modelled marginal means. In the English Channel, the median maximum sound pressure level during noise exposure was 122 decibels. This was 7 decibels greater than the before or after categories. In the Celtic Sea, median maximum sound pressure level was 111 decibels, but this was 13 to 15 decibels greater than the before or after categories. Noise category was not a significant explanatory factor for the models of dive metrics, dive duration, maximum dive depth, bottom time, and inter-dive interval. However, for adults in the English Channel, noise category and dive class were significant explanatory variables in the ascent rate of seals. For benthic dives, those that used 80% or more of the full depth of the water column, there was an increase in ascent rate of 0.09 metres per second between the before and after category. For shallow dives, those that use less than 20% of the full bathymetric depth of the water column, the ascent rate during noise exposure was 0.3 metres per second greater than the before or after categories. For pups in the Celtic Sea, noise category and dive class were significant explanatory factors in the model of descent rate. For pelagic dives, those that reached between 20 and 80% of the water column, there was a significant decrease in the descent rate of 0.05 metres per second after noise exposure when compared to during and before. A number of other studies have reported changes in the ascent rate and descent rate of seals in response to noise sources such as pile driving and sonar. This study extends that to include shipping noise. However, the direction and magnitude of change varies between all these studies. Increases in ascent rate could be consistent with surfacing more quickly or travelling over a shorter distance, and decreases in descent rate could be due to travelling more slowly or undertaking a longer path with more horizontal or vertical movement, such as swimming away. The extent to which such small changes may compromise individuals or populations is unclear, and the random effect indicated individual variation between seals. The driver of differentiation by dive class is also unknown. It could be due to methodology, for example, it is more difficult to model noise in the very shallow locations, or for pups, they showed difference in pelagic dives and not benthic dives. And pup diving behaviour is undergoing change with age as buoyancy and oxygen storage capacity develops. The proportion of benthic dives is increasing over time for these seal pups. The response seen was not always during a noise exposure event. This may be due to some error in the noise exposure predictions, but also for continuous noise sources such as shipping noise, there is a gradual increase and decrease in noise over the three categories, and no hard barrier such as might be seen with impulsive noise sources. In conclusion, high ship noise exposure events can result in an increase in the ascent rate of adult grey seals and a decrease in the descent rate of grey seal pups for certain dive types. These changes are possibly consistent with surfacing or swimming away response. The changes appear small and transient in nature, so their impact on vital rates or population stability is yet to be determined. Thank you for your time.